So we are doing a lesson 2.4, properties of angles and polygons for Math 20-2. And we're going to start off with a little bit of terminology. We're looking here at polygons. And first we're looking at defining a polygon. A polygon is a plane shape, and not plane as in airplane, and not plane as in not fancy, but plane as in two-dimensional. So it's something you draw on a piece of paper. So it doesn't have any height, it's just on a paper. And it has straight edges. So anything you draw that has straight sides is a polygon. And now we're going to distinguish polygons, different types of polygons. Convex polygons are polygons where each interior angle is less than 180 degrees. So if we look at some of these examples down here, we can see in this polygon that we have an angle here that's greater than 180 degrees. So this is not convex, but concave. And here we have another concave, and this makes this concave. So those three are concave polygons, and these below here, the octagon, the pentagon, and the triangle, are convex because they don't have any angles, interior angles that are greater than 180 degrees. Now, these are also called regular, and we're going to talk about regular polygons, but this polygon here is convex, but notice that it's not quite the same as these ones. This is an irregular convex polygon. So there's two things that we're looking at. And I'm just going to go on to my next page here. Regular polygon is a polygon that is equiangular. That means all the angles are equal, and equilateral, and that means all of the sides have the same length. So down below here we have regular polygons with 3 to 7, 8 sides. Now, I'm not going to explain where the next equation comes from, but Saul at Khan Academy does a great job describing that. So if you're interested in learning about how this equation that we're going to look at was developed, you should go and watch this video. And you can see it's a link there in the class. But all we're going to do now is look at this formula. We have an equation where we take n minus 2 times 180 degrees, and that's equal to the sum of the interior angles of a convex n-gon, so polygon. And n is the number of sides. So, and this is the interior angle. So notice in this diagram, it shows us the interior angles versus the exterior angles. Using this equation, we can determine the sum of the interior angles. So if this is x plus y plus z plus w plus v, adding all of those interior angles up. And we know for a triangle, it's 180 degrees, but for a convex polygon, we have this equation that allows us to determine the interior angles. Now, if the polygon happens to be regular, and remember regular means that it has all the same side lengths and all the same angles, we can take the sum and that's what this is, right? This is the sum, and divided by the number of sides to determine the measure of each angle. It's really important that you're clear about what the question is asking. Is the question asking for the sum? Then we use this equation. If the question is asking for the measure of each angle, then we do this. You want to not get those mixed up. Let's go and do some examples. Example 1a. Find the number of degrees in the sum of the interior angles of an octagon. Now, that octagon doesn't have to be a regular octagon. It can just be an 8-sided shape. But we know that in an octagon, n is equal to 8. So if I'm going to find the sum, I find the sum by taking n minus 2 multiplied by 180 degrees. So 8 minus 2 multiplied by 180 degrees. And we get the sum of the angle. I just pull out my calculator. And that's 6 times 180. And that gives us, 1,080 as the sum. Let's go on to another example. Example 1b. Now this is working backwards. This says, how many sides does a polygon have if the sum of its interior angles is 720 degrees? So remember, the sum is equal to n minus 2 times 180. So let's take our sum, 720 degrees, that's equal to n minus 2 times 180 degrees. Now we want to solve for this polynomial or binomial first, which means we're going to divide both sides by 180. Here that cancels and leaves us with just n minus 2. And when we take 720 and divide it by 180, we're left with 4. So 4 is equal to n minus 2. Finish this up and adding 2 to both sides, and we find that this polygon has 6 sides, and that makes it a hexagon. And you'll want to take some time to remember these names: hexagon, octagon, pentagon, etc. Okay, on to example 2a. Outdoor furniture and structures like gazebos are regular hexagons, so we've just dealt with the hexagon. In their planning, determine the measure of each interior angle of a regular hexagon. So assuming that we didn't just determine that 720 was the sum, let's just do that. We're going to find the sum of our hexagon. So the sum is equal to, and notice I keep switching the 180 in front and behind. It doesn't change the equation, whether the order of multiplication. So our sum is equal to 180 times 6 minus 4. If we calculate 6 minus 2, which is 4, 180 times 4 gives us 720 degrees. Remember that in a hexagon, that's 6 sides, there's going to be 6 angles. So to find the measure of each angle, we take the sum of 720 and divide it by 6, and that gives us 120 degrees. And let me just, I did that in my head and I'm just wanting to confirm. Absolutely. So each angle has a measure of 120 degrees. The only reason we can do this is because it's regular. Each of those angles is the same length, or the same, has the same measure, and each of the sides is the same length. On to 2b. Each of the interior angles of a regular polygon is 150 degrees. How many sides does the polygon have? Okay, now how are we going to figure this out? Well, remember that we took the sum and divided it by the number of angles, and that gave us the measure of each angle. We don't know what the sum is, and we don't know what n is, but we do know that the sum can be calculated by taking 180 degrees times n minus 2. We divide that by the number of angles, which is also the number of sides, and in this case we get 150 degrees. Now we can take and solve this for n. So multiplying both sides by n, and that isolates our n, or sorry, it removes our denominator. We have 180 times n minus 2 is equal to 150n. Well, now we've got to simplify this and solve it for n equals. So the way we're going to simplify it first is to multiply that 180 degrees in. So 180n minus 2 times 180 is 360 degrees, and that's equal to 150n. We have n terms with the variable n on both sides. We want to move them all to one side of the equation. That's negative 180n. So we're subtracting 180n, and we do exactly the same thing on this side. 180n minus 180n, that gives us 0. So we're left with negative 360 degrees is equal to 150n minus 180n. That's negative 30n. Now we can just divide both sides by negative 30. Negative 30 divided by negative 30 gives us 1, so we have 1n. And negative 360 divided by negative 30 gives us 12. And so a 12-sided figure has interior angles of 150 degrees. Actually, a regular 12-sided figure polygon has interior angles each measuring 150 degrees. And just for fun, that's called a dodecahedron. Just for fun. Let's go into an application question. A floor tiler designs custom floors using tiles in the shape of regular polygons. Can a tiler use congruent regular octagons, congruent squares, and squares to tile a floor if they have the same side length? So again, I'm not a big drawing person, but if we have a square and it has a side length and an octagon with about the same side lengths like this, can it work, right? Would that put another octagon here? And now I can draw it, but it's not a regular shape. Is this going to, right, that angle x and that angle x would have to be exactly the same. That's why I've used the same variable. Plus 90, right in there all the way around, has to add to 360 degrees. We need to find out what this angle is in an octagon, in a regular octagon. Let's calculate the measure of each angle. in a regular octagon. That's 180 times 8, an octagon has 8 sides, minus 2, all divided by 8. This is 180 times 6 divided by 8. Let's calculate that. 180 times 6 divided by 8. And so each of these is 130 degrees. Well, if this is 135 degrees, and if this is 135 degrees, is it going to fit, or are we going to end up with a little bit of an extra angle? So let's see, 135 plus 135 plus 90 degrees, does that equal 360? Let's add it up. 135 and 135 is 270. 270 plus 90, all right, it hits that magic number of 360 degrees, and so it's going to all fit together. And if we look down here, I have a nice graphic of what it looks like. So let's pull that up and make it just a titch larger. And you can see that that's what we're fitting in there. And so when we're making a pattern, we're looking to get them to fit together. We know that at the corners, they have to add to 360 degrees. Let's do another example. Can a tiling pattern be created using regular hexagons and equilateral triangles, and all of them having the same side? Well, remember, we just did a question back here. I think nope, that's the dodecahedron. All right, a hexagon, each angle in the hexagon is 120 degrees. So we don't have to do that calculation again. We know that we have 120 degrees, or some combination of 120 degrees, and we also have equilateral triangles. So let's see, equilateral triangles, remember we looked at those, and each of the angles have to be exactly the same, so 180 divided by 3, and that gives us 60 degrees. Is there a way that we can combine these to form a corner that's going to have 360 degrees around it? So we put in a corner, and let's put in a regular or an equilateral triangle. So that's going to be 60, and we want it to be 360 degrees. So I could see here, oh yeah, look, we could just put in 6 of these, and that would make our let's see, 1, 2, 3, 4, 5, and 6. That's going to create our that would work, but it doesn't exactly cover it. So we could use 6 equilateral triangles. But notice this is a multiple of 2, right? So I could take one of those out, and that would be 120. Oh, we could do that. That would be cool. And then we could put in 3, so 1, 2, 3, 4 equilateral triangles and 2 of the hexagons. Or we could put in 2 hexagons and 2 equilateral triangles. So there's a number of combinations that are possible. So yes, this is a combination that's going to work. And what I want to show you, I picked up some patterns, examples here. And this process is really a common process in forming our, in forming the quilting, where you have pieces coming together and you have to be able to put that together And so here you can see in this corner, we've got 1, 2, 3, 4, 5, 6, just like we said, 6 triangles that came together to form those corners. And we've got the same thing happening here. If we look at this one, it's kind of fun. We have hexagons and equilateral triangles right in here. So we have 2 hexagons and 2 equilateral triangles, and it works. And then you can see this star pattern, and it's doing the same thing, creating a pattern with hexagons and equilateral triangles. So it's kind of cool that these are exactly the same, right? This pattern here and this pattern here are exactly the same. The only difference is the way it's shaded, and the shading produces different shapes. So if you didn't realize it, all of those quilters out there are actually very practical mathematicians. I want you to practice, practice, practice. Always go to your textbook or your workbook, do some questions, and I will talk to you tomorrow. Bye for now.